Imagine moving a wire again perpendicular to a magnetic field as shown. It's Fleming's right-hand rule that tells us which way positive charge will get pushed, and in this case it's to the right. So if the wire was connected to a circuit, a current would flow to the right. Let's see how this works. This time we've got our thumb showing the direction the wire is moving. B is still the direction of the magnetic field, and now your middle finger is showing the direction a positive charge will get pushed, or that's the direction of current if you've got a closed loop. Now if positive charge is being pushed to the right, then negative charge is being pushed to the left. And we know that metal nuclei can't move, but electrons can, and so the electrons in the wire get squashed into the left side of the wire, leaving the left end negatively charged and the right end positively charged. But this means that there is an electric field across the wire now, and so a potential difference. This potential difference can push charges round a circuit if the ends of the wire are joined, so in fact what we have induced is an EMF across the wire. If you prefer not to think about individual charges moving, you can just remember that moving a wire through a magnetic field induces an EMF, and if the wire is connected to a circuit, a current will flow. The direction of the current is given by Fleming's right-hand rule. We can ask two questions about this EMF we're going to induce. How big will it be, and what direction will it be in? Let's take the direction first. For your A-level, you will say that the direction of the induced EMF is such as to oppose the motion that caused it, and this is called Lenz's law. But what does it mean? An easy way to think about it is to think about the trick where you drop a magnet into a metal pipe. The magnet will fall more slowly than just a piece of metal that you drop into the pipe. So why is this? As the magnet falls, the sections of the metal pipe are moving through magnetic flux because the magnet is moving past. So an EMF is induced across the pipe. This causes a current to flow around the pipe, and this current has its own magnetic field, don't forget. This magnetic field turns the pipe into a magnet, and this new magnet is the other way up to the falling magnet, and so it repels it. Now the acceleration of the falling magnet is reduced, and this causes it to take longer to reach the bottom of the pipe. This is a great example of Lenz's law. The falling magnet induces an EMF that results in a force that slows the magnet down. The size of the EMF induced depends on how quickly the wire is moving through magnetic flux. The formula is this: induced EMF equals rate of change of flux. If you're familiar with differentiating, the deltas should really be D's here. So if we move a 1 metre long wire 20 centimetres through a uniform 5 Tesla magnetic field, moving it perpendicular to the field, the change in flux experienced by the wire will be 1 Weber. And if this takes 2 seconds, and we're moving it at a constant speed, we will induce a constant EMF of 0.5 volts. Notice that if we stop moving the wire, the EMF will drop to 0 because the wire won't be moving through the field anymore, and so the change in magnetic flux will be 0. Also note that if we move the wire parallel to the field, there will be no induced EMF because again the change in flux will be 0. It's time to see how all this relates to rotating coils in magnetic fields. Look at the diagram and think about how much magnetic flux the red side of the coil is moving through between the different letters. Remember that if you're moving parallel to the field, you'll induce zero EMF, and if you're moving perpendicular to the field, you'll induce maximum EMF for that field and that speed. Hopefully you can see that the wire is moving through less field between A and B than between B and C, and then moves through even more between C and D. If the wire is moving at a constant speed, this means that the wire is moving slower through magnetic flux from A to B than it is from B to C. The wire is moving parallel to the field at A and G, so no EMF induced there. Then at D, it's moving perpendicular to the field, so that's where the induced EMF will be maximum. Putting this all together, we get no EMF at A and G, max at D, getting bigger from A to D, then smaller again from D to G, and the exact shape is a sinusoidal wave. If we continued, we'd get the same pattern as the wire moves round the other side of its rotation, except that the EMF will be in the opposite direction, which will be negative on our graph.